Swayam Prabha. Digital India. Educated India.
And today I'm going to focus on the CO2 activation and utilization. So once we capture CO2, either we can store it or we can utilize it in various ways such that we can get useful chemicals, fuels and other stuffs. Right. So, and the particular aspect of the CO2 activation and utilization that I'm going to focus is a thermocatalytic route. So we'll have catalytic conversions where the CO2 in addition to other reactants will be converted to some value-added products which can be utilized further. Okay, so to start with, little bit background why we need to do it. So at present, more than 80% of the energy need for the human community to survive is coming from fossil fuel. And if I put numbers to it, to achieve that 80% of energy requirement of the total energy that we are spending these days, we are consuming about 20 million tons of coal, 12 million tons of oil and about 10 billion metric cube of natural gas. And when we are consuming these things, we are producing about 100 million tons of CO2 every day. Now where this CO2 is going? Mostly they are going to the atmosphere. And if we look at just 1 year of data, how the atmospheric CO2 concentration has changed from 24th November 2023 to 25th November 2024, which is only three days back, it has increased by 3.01 ppm, which is 0.71% higher than the previous value, what it was a year ago. And if we look at a longer scale, we can see for a couple of centuries, starting from 18th century to up to 19th century, the CO2 concentration was pretty stable in the atmosphere, which was in between 250 to 300 ppm. But after the start of the industrial revolution, we have increased CO2 concentration. Now at present, we are above 400 ppm levels. And all these CO2s are causing climate change and other issues to the human society. So to address that, we need to keep that temperature rise below 2 degrees Celsius as compared to the pre-industrial era, or to be specific, it should be within 1.5 degrees Celsius as compared to the pre-industrial era. So how can we achieve it? To achieve it, different countries and continents across the whole world, they have devised policies to mitigate CO2 emission, as well as to find out new ways where we can utilize this CO2, not just capture it and store it, such that the overall process efficiency can be improved, such that we are gonna the net generation of the CO2 is going to be low. Okay, so for this target, most of the countries their target to achieve this net zero is by 2050, whereas China it's 2060 and for India it's 2070. But in addition to that, we have another target that to reach the carbon level of 2005 by 2030. So what the amount of CO2 that we were generating in 2005, we should come back to that level by 2030. That's the target. And the biggest question is how we are going to do it. Okay. So for that, I just put one box here that says we need to find new ways for production of energy and chemicals. Now, what do I mean by that? That new ways, and what are these new ways? Okay. So at current, we are dependent on the fossil fuels, right? It can be coal, natural gas or petroleum products. Okay. And it's very difficult to replace all these things, especially in a case where more than 80% of our energy requirement is coming from these fossil sources. And why is it hard to replace? That's because they have huge energy densities. Number two, they are chemically stable under normal conditions. And number three, they are easy to store and transport. So what we can do is that, can we convert CO2 in some way such that we can produce the same chemicals which we are producing from the fossil fuels, the same chemicals and the fuels. Okay. So that means we have to reduce CO2 with some additional co-reactant, which is typically hydrogen in our case. That means CO2 reduction with hydrogen to produce some chemicals and fuels, and in return, this hydrogen should be generated from a renewable energy source, not from the conventional fossil fuel. Because in that way, for 1 kg production of hydrogen, we are generating more than 10 kgs of CO2. So we are not going towards the carbon dioxide net zero, rather we are generating more carbon dioxide. So we need to produce hydrogen from the renewable energy sources. One example is water splitting by use of some renewable energy sources like solar energy or wind energy, such that we can do water splitting and get hydrogen, and that hydrogen can react with CO2 in presence of a catalyst to form some fuels and chemicals. And that fuel and chemical can be transported to different sectors. It can be a transportation sector, it can be a domestic sector, or it can be an industrial sector where it can be used, and after their end use, more CO2 will be generated, but those CO2s will again be captured and then sent for the reaction for conversion to fuels and chemicals again, such that it closes the full carbon cycle. So that's the overall idea. So we'll just look at what are the different pathways for CO2 hydrogenation and what are the different products that we can form at our current scientific level. So there are many different products. One is methanol, there is methane, CO, there can be some higher alcohols, there can be dimethyl ethers and all these things. And all these chemicals that you are seeing are fine chemicals that we use and are currently produced by the petrochemical routes, or these chemicals serve as the intermediates for producing the final chemical or the fuel. Okay, and all these chemicals can potentially be produced by CO2 hydrogenation routes. And here I have I mentioned a few of the catalysts which are selective for different reactions under different reaction conditions like temperature, pressures and all these things. Okay, despite all these scientific advances, only a few of these processes are at the commercially viable level. Okay, because there are several challenges. The biggest challenge is being CO2 is a very stable molecule. The bond dissociation energy for carbon and oxygen is very high. That means we need to put a huge amount of energy to break that bond such that it can be converted to the desired fuel or chemical. Okay, and for that we need harsh reaction conditions. It cannot be a very gentle reaction conditions like low temperature or moderate pressure or low pressure where the things can happen. That means the CO2 conversion to the fuels and chemicals can happen. And because of these harsh conditions, we require huge amount of energy input. Okay, that's number one. The number two, because of the harsh conditions, the catalyst that we are using for conversion of CO2 to different fuels and chemicals are not going to stay stable for a long hour of operation. Okay, now there are other issues like catalyst deactivation. The catalyst deactivation simply means the catalyst is not performing as it is supposed to perform. That means when we start with the fresh catalyst, it's giving us a performance X, and over the time the performance X is going down and down. That's what we call a deactivation. Okay, and this deactivation can happen by many different ways, and these are the few things that I have highlighted here. One, that is by poisoning of one of the byproduct, which is water. Because all these reactions on the schematic that I showed in the previous slide, they have one major byproduct which is water, which is generated along with the desired fuel or chemical that you want to get. Okay, and because of the presence of water at harsh conditions like high temperature and high pressures, these catalysts deactivate and they change their structure in the course of the time during the reaction when they are exposed to these conditions for long hours. There is something called active metal sintering. I will talk about it in a couple of slides what is active metal sintering, but in simple words, active metals are the one which are responsible for the chemical conversion of CO2 to our desired product, and sintering is something that agglomeration kind of thing. We have a dispersion of active metals, and dispersion means larger surface area compared to the volume. That means higher amount of catalytic reactions, and when they sinter, the volume increases, the size increases, and the available surface area decreases. That means the reactivity goes down and down with respect to time. Okay, There is something called coke formation. Just because we are implementing high temperature and pressure conditions, some of the carbon dioxide, they are converted to atomic carbon species, and these carbon species are not helping during the reaction. They can form a coat on the active metal, or they can form a coat or they can just block the pores of the catalyst, which are responsible for giving higher surface area and hence promotes the reaction. Okay, the last one is the overoxidation. Just because CO2 breaking brings out formation of one atomic or active oxygen, that active oxygen can oxidize the active metal. We want that metal to be present in metallic state because it has a particular electronic configuration that helps in conversion of CO2 to fuels and chemicals. But when that oxygen is produced because of CO bond breaking of the CO2 molecule, it oxidizes that metal to some higher oxidation state, and the electronic configuration change, and because of that change our activity changes, which in many cases it decreases. Okay, but in some cases it helps. That also we are going to discuss towards the next part of the lecture. And the major problem is the selectivity. The selectivity means when we are trying to convert CO2 in presence of hydrogen to some desired product, say for example methanol. Now along with methanol we are seeing a bunch of other chemicals or fuels which we do not want. Now that means the percentage of the desired product in the outlet of the reactor are not great. Okay. Now, how does this selectivity is a major challenge for practical implementation of this process, because in industry, huge amount of energy is spent in separating the product. If we have a low selectivity, that means we have to spend more and more energy to separate the desired product from the undesired product. Okay, that means we are spending more energy, means we are generating more CO2. So this process is not any more carbon neutral or carbon negative compared to the current or the existing processes. Okay. Now, if we look at all these things, now what can be done such that these processes can be improved further and they can be scaled up to a commercial level. Okay. One major thing is that we have to design a better catalyst. We need a better reactor and process conditions. Right, and all these things can be achieved by getting some key information. Now all these information are: what is the nature of the active site that does the actual chemical transformation of CO2 to a product, because what happens is that our catalysts are not ideal. When we synthesize catalyst or prepare a catalyst, there are many different kinds of active sites, those are present on the catalyst surface. And each of these sites contribute to a different part of the reaction. So some of them are favorable for production of the desired product, and some of them they promote the production of the undesired product. So if we identify which one is the site that promotes the desired product formation, what we can do is that we can populate that kind of site and we can suppress the other kind of the site that promotes the side reaction, and thus we can increase the overall activity of the catalyst, right? Similarly, we need to know the nature of the reaction intermediate. When the reaction happens, it's not just go from a molecule A to the molecule B, it goes through some intermediate step. And depending on the nature of the site, temperature, pressure and all these conditions and the co-reactants, the nature of the intermediate will be different. And that intermediate defines which final product we are getting. So if we can identify the right intermediate that goes to the desired product, we can formulate the process, the reactor, or change the process conditions and all, as well as tune the catalyst to promote the formation of that kind of intermediate, while we can suppress the formation of any other intermediate which are not helping us in generating the desired product. Okay. And the overall reaction mechanism and kinetics. So the reaction mechanism and kinetics are important. That's because these information are crucial for the reactor design. Okay. The majority of our talk is going to focus on how to understand the CO2 activation and the hydrogenation pathways in a thermocatalytic route, such that we can design a better catalyst. And towards the end, we will talk a little bit about different type of reactors that can be included to help these processes, and some of the novel techniques. Instead of conventional fossil fuel, can we use some kind of electrification process or renewable electrification processes which are dependent on the renewables, such that we can ultimately decrease the process energy load, which ultimately helps the reduction in CO2 generation for all these processes. Okay, so that's going to be the overall outline. Since we have attendees from different backgrounds, so I will just give a very brief overview of what is catalytic reaction, what is a catalyst, and what are the active site. And then once we have those kind of information, we will talk about the CO2 activation routes. Then we will talk about different CO2 hydrogenation reactions. Especially we will focus on those reactions which produce the C1 products. C1 means the carbon 1 products, and these can be methane, methanol, and in the reverse water gas shift we produce CO. And then finally dry reforming of methane, where we produce CO plus hydrogen. Okay, and then we will talk about different mechanisms of catalyst deactivation, and specifically we will focus on the coking, and then we will talk about how we can suppress the coking such that our catalyst can be active for long hours of operation. Then we will talk a little bit about the reactor design, such that all these reactions that we are talking here are going to be favorable and we can get the higher amount of desired product. And we will discuss a little bit on these noble electrified processes, where instead of using the conventional fossil fuel to do the reaction, we take the energy from the renewables and we provide it to the reactor through microwave heating or joule heating, such that we decrease the overall process energy load. Okay, and finally, apart from the C1, we will talk about a little bit about the C2 products and how CO2 can be utilized in other thermocatalytic routes to produce other products, and some of the advanced concepts like chemical looping reaction mechanism, where we can have one material which will capture and convert CO2 at the same time in two parts of the reaction, which is the looping mechanism, followed one by the other, and then coming back to the first phase again. Okay, so that's going to be the overall outline of our lecture here. Okay, so we will start with catalytic reactions. So catalytic reactions are nothing but chemical transformations. So what is this chemical transformation? We have certain molecules which we call reactants. They have bonds which hold together the atoms of the molecule, and then catalytic reactions means we break such bonds and we form new bonds. Okay, that's the chemical transformation. Now, because of the application of heat, these bonds can be broken and then they can be converted to a different product by formation of new bonds. But for that, we have a huge energy barrier, and this energy barrier is overcome by getting the energy from the temperature, the heat. Okay, but in presence of catalyst, because of this particular electronic configuration of the catalyst that it has, it can lower that barrier by a significant amount. Okay, such that we don't have to put that much of energy. That's the nature of the catalyst. It just promotes the reaction in the forward direction. Okay, but at the same time it also promotes the reaction in the backward direction, as you can see. But how does these heterogeneous reactions happens? There are 7 steps that has been outlined by Bodor, and those who have gone through undergraduate chemical reaction engineering course, they know all these 7 steps. But here, to simplify the case, in the limiting case of no heat transfer and mass transfer limitations, we have 3 major steps that takes place during a catalytic reaction. Okay, what happens? We have gas phase molecules, which are the reactants. They adsorb on the surface, they stick to the surface, and they stick because of the nature of the sites that is present on the catalyst. Then on the surface, they undergoes the reaction, and then whatever product is formed, they desorb into the gas phase. So adsorption is one phase, surface reaction is the second phase, and desorption is another phase. Okay, and if we look at the energy diagram, we have little bit of energy barrier for this adsorption, then probably higher energy barrier for the reaction, because most of the heterogeneous reactions that happen in our community, 75% of those are surface reaction limited. That means the barrier for the surface reaction is the highest as compared to the adsorption and desorption of the products. Okay, and if this is very clear to all of you, I'll just put another concept here which we will be using towards the end of the lecture, that is called a Savartier's plot. Okay, and it shows the binding strength versus the rate of the reaction. Okay, so what happens is that the binding strength is nothing but when we have this surface activated species present, how strongly they are bound to the catalyst surface. Okay, if they are bound really weakly, that means only a very small amount of the gas phase molecules are present on the surface and the overall reaction rate is low. If they are bound too strongly, then the surface reaction intermediates which are formed after the reaction on the surface of the catalyst, they cannot dissolve. So we cannot see the final product, and hence the overall rate of reaction is again low. So we need to have an optimum amount of binding energy such that it's strong enough for the gas phase molecules to be adsorbed on the surface, but not so strong at the same time such that the formed species are not dissolved to the gas phase. Okay, so that is clear. Next, look at the nature of the active site. So this is like a very crude model of how a catalytic site or a catalyst looks like. And here I am giving you an example of metal catalysts. Now typically these metals, because of their outer shell electronic configuration, they activate CO2 and H2 at the same time, and the reactions can happen on these metal sites and we get our final product. Okay, but like we said, it's a surface phenomena, so we need to have more surface area to increase the overall reaction rate, and most of these metals are precious, so we want to finely divide these metals on the surface as that we can get maximum out of it, right? So how do you do that? We take a very high surface area support material, and then we try to deposit all these active metals on the surface, and because of the size of the active materials, we can have different surface to bulk ratios. Okay, we can have isolated sites, that means just one atom of this active metal are present on the surface. We can have small oligomers, which can be like a dimer, trimer or a tetramer type of species, and if you notice, these are still two-dimensional species. They are still formed on the XY plane. They haven't gone to the Z plane. Okay, but if we still increase the loading, now we are going in the third dimensions, and here we are forming small clusters. Now what is the difference between this and this? Here all the atoms are interacting strongly with the support, whereas some of the atoms here are not so strongly bound to the support, and hence the sites which are bound to the support has a different electronic configuration than the site which are not in direct contact with the support. Okay, if we further increase the loading, we can have polycrystalline clusters. That means now we have the crystal size big enough, or the cluster which has the number of active metal particles are high enough such that we can form different ending geometries. It can be a 110 plane, 111 plane or 100 plane, and depending on this ending geometry, we have a different atomic configuration of these atoms on the surface that is exposed to the atmosphere or the reactive atmosphere, and they can perform differently. And beyond that, we have like big nanoparticles, and we can have bimetallic alloys where instead of just one active metal, we have multiple active metals present. Okay, so this was about all the active metals that is present on this support, and the supports are typically high surface area oxide supports, but the supports can have some electronic configuration which can also participate in the reaction, right? So that's what we are going to see in the next slide, and this is a simple example of a noble metal that is deposited on oxide support, which is tin oxide, and we can see like what we think. These oxide structures are not ideal in reality. They have many different kind of terminal sites. For example, there can be a vacant sites where oxygen is not present. There can be a coordinatively unsaturated sites where the tin atom is not present. There can be some oxygen which are not bound to the tin so strongly that this oxygen can participate in the reaction. There can be hydroxyl groups, which is nothing but these OH ending species on the surface, and they can participate. And all these things contributes to either it's a redox site, an acid site or a basic site. and nature of these sites define how this chemical transformation is taking place. So that was just the broad background of how a catalyst look like, what is a chemical reaction, what can be the nature of the active site and all. Okay, so with this broad background, we will go ahead and see how the CO2 is activated on these metal supports, and then what are the reaction intermediates formed, and when we add hydrogen, how the reaction pathways change, and then all these things. Okay, so interestingly, the CO2 can be activated on the noble metal that we deposit as well as on the oxide supports. Okay, it can be activated on the vacant site of the oxide support, it can be activated on the oxygen species of the oxide support or the hydroxyl group of the oxide support. And let's see when it is activated by the hydroxyl group versus the oxygen on the oxide support, what are the different intermediates that we are seeing. Okay, so the first thing is the reaction between CO2 and the surface hydroxyl group, and like I mentioned, these hydroxyl groups are nothing but the OH groups that is present on the surface of the catalyst. Now if you look at this schematic here, these OH groups can be of different types. It can be an bridged OH where the oxygen is connected to two metals at the same time, or it can be an isolated or terminal OH where the OH is connected to just one metal, right? So what happens when a CO2 comes near this kind of the OH group? The CO2 first gets a bent configuration where one oxygen is connected to the metal atom because of electronic transition, this ligand that forms between the metal and the oxygen, and then there is an oxophilic attack by the oxygen atom of the OH group, because this oxygen atom has a lone pair of electron, and that lone pair can attack the carbon of the carbon dioxide, because in the carbon dioxide the carbon is in a delta plus charge where the oxygen are in the delta minus charge. Okay, so that electrons that attacks this carbon, and then we form a carbonate type of species, and in particular this is a bidentate carbonate. That's because it's anchored to the surface with two sides, this kind of configuration. Then what happens if we have a neighboring OH group? Then that oxygen from the neighboring OH group that attacks to the hydrogen species, and we have a carbonate species and an adsorbed water that is present on the surface. Now at a later stage, the oxygen which is dangling in the reaction environment, it's having an extra electron that can attack the edge of this water that is present on the nearby surface to form a bicarbonate type of species. Okay, now you can see depending on the type of OH group that is present on the surface, we can have different reaction intermediates. Now why I am saying these things? Because all these reaction intermediates, like I mentioned at the beginning of the lecture, are going to end up in different products, and if we identify the right reaction intermediate and populate those, then we will increase the selectivity towards our final product or desired product. Okay, now let's see, like I mentioned, if there is a bidentate kind of or bridged kind of OH group versus a terminal OH group or isolated OH group, what is the reactivity of these different kind of OH groups? Okay, this is a simple experiment on a zinc oxide kind of species where two different OH groups are present. One is a bridged OH which is identified by this 3665 centimeter inverse Webb number from the infrared spectroscopy. We don't need to go too much into it, just a simple thing is that infrared can identify the molecular species because of their unique vibrations. This OH has a particular vibrations and the IR has a frequency of 400 to 4000 centimeter inverse Webb number. Then when we get the right amount of energy, that amount of energy is absorbed and this bond vibrates at a very high rate, and that's how we identify this kind of species. Okay, and this is a different spectra. Different spectra means we look at the spectrum of the pristine catalyst or the zinc oxide where there was no CO2, then we add CO2 and we subtract it from the original thing. That means the sites or the OH group in our case which are consumed will show a negative intensity. The sites which are not consumed or the OH groups which are not consumed, they will not show a negative intensity. Okay, and out of these two hydroxyl groups that is present on zirconia. One is bridged hydroxyl, another is the terminal hydroxyl. We see only the terminal hydroxyls, they show a very strong negative peak. That means they are the sites which are more reactive towards the CO2 and not the bridged OH groups. And this type of experiment gives us an idea. If we want to have a higher activation of CO2 on zinc oxide type of material, then probably we'll have to populate the terminal OH and not any other kind of OH. FTR data. Okay. So next thing is that now we know that how CO2 reacts with the surface hydroxyl groups. Let's see what are the other types of species that is present on the oxide support that can activate CO2. And one other thing that we am going to discuss is the surface oxygen atoms. Okay, this is a simple metal oxide, nothing but metal oxygen bonds and terminal metals and oxygen atoms on the surface. So what happens is that we have CO2 that comes in a bent configuration, and again O2 attacks the carbon of the CO2 molecule and we form a monodentate carbonate type of species here. But now what happens is that if we have a significant amount of OH group that is present on the same metal oxide, then instead of a carbonate, the oxygen of the carbonate will attack the hydrogen of that OH group, and now we have a bicarbonate type of species present. So that how it defines, like having an OH group on the surface versus there is no OH group on the surface and the reaction intermediate is different. In one case it's carbonate, in another case it's a bicarbonate species, and that also tells us whether to keep these carbonates or hydroxyl groups on the surface depending on whether bicarbonate is our active reaction intermediate versus being carbonate being our active reaction intermediate, where we will not keep any hydroxyl groups. Okay, so that was about the activation of CO2 on the metal oxide surface. Now let's see how does a metal react when it is exposed to a CO2 atmosphere. Okay, because metal is another type of active sites in our catalyst that is present, right? So for that there are several examples. The first one I will look at as a pristine metal. That means the metal is clean, it's at low temperature, there is no other species present on the surface of the metal. Under such conditions, the CO2 when it gets activated, two different types of activated species are formed. One is just the neutral CO2 which is linearly bound, it's just adsorbed because it's a low temperature where adsorption is more favorable at its metal surface. And another one is an anionic CO2 where some electron transfer from the metal to the CO2 takes place. Okay, and when we take this activated complex, CO2 complex on the metal surface to high temperature, instead of keeping it at low temperature, if you take it to high temperature which is the reaction relevant temperature, it's only those anionic CO2 that dissociates into one carbon monoxide and one surface oxygen or the carbonate. Okay, now we will see when surface oxygen is there, when carbonate is there. Okay, and then there are also different things that we have to keep in mind. One of them being the structure sensitivity, which is a very important part in this type of catalyst. What structure sensitivity means, for the same metal, if I have one particular plane that is exposed to the CO2 atmosphere versus another plane, now not all of them are equally reactive or not all of them equally activate the CO2. Okay, so this is just one example that I am showing, is that the CO2 adsorbed in a molecular fashion like this one, a neutral CO2 on nickel 111 and iron 110 surface, whereas for the same nickel, if instead of 111 I go to a 110 surface, now CO2 is dissociatively adsorbed. That means CO2 is already activated to CO and surface oxygen. Okay. Similarly, Fe110 it's molecularly adsorbed, whereas iron 111 and 100, which is the cubic structure, the dissociatively adsorbed. Then there are some density functional theory calculations which show that which metals are more reactive or are more active towards activation of CO2 molecules. So what happens is that some of the metals like iron, cobalt and nickel, they have small amount of electrons, like low number of electrons in their outer d orbitals, and they can donate that electrons, and they can, with those electrons, attack the carbon of the carbon dioxide and doing a charge transfer, such that those species are highly active towards the CO2 activation. Whereas some of the other species like copper, palladium and platinum, they have almost filled d orbitals. Because of the filled d orbitals, they do not prefer to share more electrons, such that they are not as active as these metals towards CO2 activations. Okay, and this is graphically plotted here, where we are seeing the amount of electron that is transferred to CO2, the more negative charge that the CO2 gets. So we move in this direction. More electron is transferred to CO2 means more negative charge, and when we are getting more negative charge on the CO2, we are seeing something which is called the bond length of the CO. Now, shorter the bond length of the CO, stronger is the bond. When we elongate that bond, that means it's a weaker bond. Weaker bond means it's easier to dissociate compared to a stronger bond. That's what. When we have more charge on the CO2 with the compounds or with the elements which can supply electrons, we have elongated CO bond. That means the tendency for CO activation is higher and higher as compared to the other ones where we have lesser charge and shorter bond, which is a stronger bond. Okay. Now, this was on the pristine metal surface. That means there was no other element present when CO2 is adsorbed. But there can be different cases. Okay. Now, when CO2 is adsorbed, it dissociates into CO and surface oxygen. So, this surface oxygen is now going to hamper the next CO2 activation. Okay. One molecule of CO2 comes, it dissociates into CO and surface oxygen. Now, surface oxygen stays there. When the next molecule comes, it not just sees the pristine surface, it sees an already pre-adsorbed CO as well as the atomic oxygen on the surface. Now, here I am just showing one experimental data which is from X-ray photoelectron spectroscopy, which gives us an idea about the oxidation state of different species, right? So, what happens is that here we are adsorbing CO2 on a metallic nickel catalyst. Okay, and then when we adsorb, we see that under ultra high vacuum conditions, when there is no gas phase CO2 present, we do not see any kind of CO2 signature in the XPS spectrum, and at the same time we see only the presence of metallic nickel on the surface, okay, or near the surface layers. But as soon as we go to room temperature and introduce some amount of CO2, which is 200 millitorr amount of CO2, we see that now apart from the nickel 0, which is the metallic nickel state, we have formation of nickel oxide as well as nickel carbonate. And why is it happening? That's because once the CO2 is adsorbed on the surface of nickel dissociatively, that means CO2 is getting dissociated to CO and oxygen, that oxygen is oxidizing nickel to nickel oxide. Okay, that's why apart from just the metallic nickel, we are seeing signature for the nickel oxide here when CO2 is adsorbed on the surface. Now that apart from nickel, since we have nickel oxide will also participate in activating CO2, just like we saw the metal oxide, right? Couple of slides back. And we are going to observe a carbonate type of species if there is no hydroxyl groups present, correct? And that's exactly what we are seeing here. So when this is exposed, the surface of nickel metal does not stay as metallic nickel anymore. We have nickel oxide, the coat on the metallic nickel, and on the nickel oxide, further CO2 activation gives a carbonate type of species, which is the nickel carbonate in this case. Okay, so this is how the CO2 is getting activated by change of the catalytic active site. But for our hydrogenation reaction, apart from just CO2 or this atomic oxygen on the surface which is formed by the CO2 activation, we will have some activated hydrogen, because this is a hydrogenation reaction and hydrogen is our co-reactant, right? So let's see, when we have a surface which is pre-adsorbed with atomic hydrogen or activated by hydrogen, and then we are allowing the CO2 to come, what kind of intermediates that we are forming. okay, because this is the simulation of our experiment, because in our experiment we have both CO2 and hydrogen and not just CO2, okay. So this is again an IL spectra, this is an XVS spectra again on carbon 1s bond. We don't have to look at all these things, let's just focus on this inset of this figure. So the top one here is when we send some formic acid to the nickel 110 surface, we form some amount of formates, and these are the signature of the formates, like a particular binding energy that is formed. At the same point, this bottom spectrum is the one when the catalyst surface is pre-covered with hydrogen, and then we are allowing CO2 to interact with that hydrogen pre-covered nickel 110 surface, and then we are getting a similar kind of binding energy spectrum from the XPS. That explains that when hydrogen is pre-adsorbed on the surface where we are going to do the CO2 activation, now we are forming the surface intermediate, which is the formate species. Okay, so we found there was carbonate, we found there was bicarbonate, we found there was activated CO and activated oxygen, and now we are seeing there is also formate. So now see, there are so many intermediates that can form depending on the nature of the catalyst and the type of the sites that is present and the surface nature. That means it's metallic or metal oxide, it has OH groups, or it does not have OH group, or it is pre-covered with hydrogen or not with hydrogen. Okay, now the idea is how to distinguish all these species. If we cannot distinguish all these species, then we cannot identify them, like pin down those species, and then we do not know which one is going to the final product or the desired product, right? So again, IR spectroscopy is very powerful in this matter along with other things, and IR has been widely used to find this kind of species. Okay, so we have different configurations of carbonate. This is monodentate carbonate, that's because it's anchored with only one oxygen to the metal sites. There are bidentate carbonates because it's anchored on a slightly upside down fashion where two oxygens are connected to the metal and only one oxygen is dangling on the reactive atmosphere. And then we have breached carbonate where two oxygens instead of connected to one metal now at two different metals. Okay, now there is something called from the IR, well actually before going to that, let's just look at these bonds. Okay, these CO2 double bonds here, here and here. Okay, since there is a bond, there is some vibration associated with because of the thermal motion, right? And IR can detect that vibration, and all these bonds have a signature fingerprint of those vibrations, and from these vibrations we can identify which one is what. Okay, now these vibrations can happen in different ways. I will just give example on this one. So this CO bond and this CO bond, they can either elongate or shorten at the same time or at the different time. Same time or different time means they can elongate or shorten in what you call it is like a okay. I'll just give you an example. So both the bonds are shortened at the same time, or both the bonds are elongated at the same time. Okay, so if I give you an example, if you consider my head to be the carbon atom and my fists are as the oxygen atom and my hand as the CO bond. Okay, it can happen like a shorten and elongation at the same time. This is called a symmetric stretching. If it happens like this, it's called asymmetric stretching. Okay, and IR can distinguish between the symmetric stretching and asymmetric stretching. Okay, now if that wavelength difference between the symmetric and asymmetric stretching is about 100 centimeter inverse wave number, then we have a monodentate carbonate type of species. If that is about 2 to 300, that's a bidentate carbonate, and if it is more than 400, then we have a breached carbonate type of species. This is just an example how IR can be utilized to distinguish between different kind of surface intermediates, so the reaction intermediates that is present on the surface. Okay, and then I'm just giving okay, so here is the one. So at the same time, and this is like a different fashion that I was just talking about, and here we have a table of different metal oxides, which are typically used for CO2 hydrogenation reaction. At the same time, the assignments for this carbonate species, the asymmetric nu A and the symmetric, that is nu S, and you can see the difference, and from that we can identify which species is there on the surface. Okay, so that's there. Okay, so we talked about CO2 activation on metal oxide. We talked about CO2 activation on metals, and then we talked about identification of the reaction intermediate. Okay, physisorption is a different thing. Reaction cannot happen without chemisorption. Okay, that's the very first step. Okay, now all these basics have been laid out how CO2 is activated. Now let's see when CO2 is hydrogenated, what are the different products that we form. So we are not going into detail too much into the reaction mechanism at present, but I will just give a broad overview of these things. But let's first look at what are the different C1 products that can be formed from the CO2. So this is an overview where CO2 is reacted with hydrogen to form different products. The first reaction what I am showing here in this red color is CO2 methanation. That means CO2 and hydrogen reacts to form methane, and obviously water is a byproduct of this reaction. And why this reaction is important? Because it's called a power to gas technology. That's because even if we are successful in generating huge amount of hydrogen at present by water electrolysis, and that electricity coming from the renewables, it's still a challenge to store and transport that hydrogen. Okay, what we can do is that we can use that hydrogen and react it with the CO2 that we captured from the atmosphere, and we form methane. Right now, methane is a natural gas. It has a well-established distribution network. So hydrogen can be transported to different sectors within the continent or the country as methane. Okay, that's why the power, which is the renewable energy, is now converted to the gas, which is the methane, by the CO2 methanation reaction, and it can be distributed. Now, methane is a fuel, and it can be used in multiple applications. It can be just used as a fuel to burn to provide heat or energy in industry. It can be used in internal combustion engines. There are companies which are developing internal combustion engines that can run on methane. Okay, yes, we will capture those CO2 and then react it again. So that will close the carbon cycle. Instead of taking more carbon from the fossil, the idea was to hydrogen is from water splitting. That is there. Yeah, I understand. What I am saying is that, well, there is definitely a huge mismatch between the amount of CO2 that we can capture today and the amount availability of hydrogen is a different thing. But then again, yeah. So, well, hydrogen. I mean, if this what you call it is a water splitting is successful with the renewable energies, then we can get hydrogen, right? Steam metherming, steam. Okay. Carbon is the basis of our life. No. Hydrogen will provide us energy, but not chemicals, right?
No. The thing is that in industry, what we are looking for, if you produce more green hydrogen, we will come out of the CO2. So since we are not able to produce more green hydrogen, that's why we are having the more CO2. Because since we are using only the crude oil and the natural gas, so that is the where we are source for the production of more CO2. So once we have only the directly hydrogen, then where is the chances of coming the CO2?
Because we are producing. So the point is, even if you are producing, okay, so two steps. Number one, the CO2 is not produced just from the hydrogen, right? Because of the hydrogen production. We have a bunch of different. Correct. That is our fossil fuel. Okay. So your question is, if we have sufficient amount of hydrogen, then we are not producing CO2, right?
No, we are not. Once we have the sufficient amount of hydrogen, everything from hydrogen, then we may not have the more amount of CO2.
Yeah, that's I'm saying. We cannot have everything from hydrogen, because carbon is our basis for life. Okay, hydrogen can give us energy, that is there. Okay, but for chemicals, we need that carbon, right? for specialty chemicals, for cosmetic products, for polyethylene, the plastics. I'm still trying to understand your question. So my point is, hydrogen will give us energy, right? But we need carbon. We need carbon for chemicals and other stuffs like plastics we are using, polyethylene, polypropylene and all these things, right? For that carbon, currently we are relying on the fossil sources because that's our only source of carbon at present. So we are trying to replace that with the atmospheric CO2 that we are capturing. Okay. Okay, we'll discuss more. Okay. So the other part why this reaction is important is that for the extraterrestrial exploration. Okay. Currently we are going for space exploration and all our rocket engines are hydrogens. Okay. So what happens is that if we want to explore a long distance, we cannot just rely on the hydrogens because we have only limited amount of the fuel. Okay. What we can have is that we can have a methane engine instead of a hydrogen engine. So we can send the exact amount of fuel required, say for one example from here to Mars, and then we have CO2 abundantly available there as well as hydrogen, which is the most abundant species in the universe. And if this process is developed, we can generate CH4 on site, which will serve as the fuel, and water, which is the byproduct, can serve as the life sustaining element there. Okay. So for these things also there is huge interest not just in ISRO but also in NASA to develop catalyst and reactor at small scale, modular scale, such that we can convert CO2 and hydrogen to methane for all these purposes. So there are also other C1 routes, another being methanol. So here we are converting CO2 to liquid chemicals. Now this is a platform chemical, methanol, and methanol can be converted to many specialty chemicals and can be used as a fuel. Okay, and it can be used as the energy storage and carrier because it can capture so much of hydrogen and can be transported from one part to the other. There is another reaction which is reverse water gas shift reaction. In reverse water gas shift reaction, it's a simple reaction between CO2 and hydrogen that produce CO and water. Now CO being more reactive than CO2, there are already established industrial processes where CO is reacted with hydrogen in a Fischer-Tropsch method, and you can get long chain hydrocarbon fuels. Those can be aviation fuels, jet fuels, and diesel fuel ranges things. Okay. Another reaction is the dry reforming of methane. Here we are not taking help from hydrogen, but rather here CO2 is reacted with methane, which is another greenhouse gas, and there is methane leakage from everywhere in the whole world. Okay, and when these two greenhouse gases react, they form CO and hydrogen, which is nothing but the composition of the syngas. And just like here, we are taking CO and reacting with hydrogen to form chemicals. Here we have CO and hydrogen already produced as the product of this reaction, dry methane reforming. And then at one point we are utilizing two greenhouse gases, and at the other point it just produces syngas, which can take this Fischer-Tropsch, Rouse and beyond, which are already established industrial processes for production of chemicals and fuels. Okay. Now let's look at what are the reaction mechanism for all these things. So for all these reactions, there are multiple reaction mechanisms, and believe me, this is like the most simplest thing that I'm showing here. What happens in reality is way more complex. Okay, simple redox pathway is where the CO2 is getting activated on the surface, which is shown by this orange color here, which is activated CO2 that dissociates into CO adsorbed and oxygen adsorbed, and then this CO adsorbed can just dissolve to the gas phase to form CO, and this is the most likelihood pathway for the reverse water gas shift reaction. Okay, there is the gray path, which is the CO methanation path, where we reach methane, where this CO2 goes to CO, goes to carbon, and then we hydrogenate it step by step, that is CH, CH2, CH3, and then finally CH4. Okay, similarly we have the carboxylate pathway and a format pathway. So in the carboxylate pathway we have CO2 where we attach one hydrogen to form a COOH type of species, which gives off one oxygen to form COH and further hydrogenate to form methanol. And there is a parallel route for methanol formation, which is the carboxylate pathway, and there is a huge debate going on in the literature whether methanol by CO2 hydrogenation follows a format pathway or a carboxylate pathway, and it's not resolved yet. Okay, so here instead of a COOH type of species, we form a HCOO type of species. Okay, this HCOO after one oxygen abstraction gives FCO, and then further hydrogenation goes to this point. Now, dry methane reforming, which forms CO and hydrogen from CO2 and CH4, that just follows typically the reverse pathway for the CO2 methanation. So we start from CH4, we get or we abstract hydrogen, we get surface carbonaceous species, and then we add one oxygen to get CO, and similarly, since we are abstracting all these hydrogens, they can combine to form molecular hydrogen and dissolve to the gas. Okay, so this is the simplest reaction pathway, and then let's just look at what are some of the challenges in all these reactions. For that, these reactions, most of these reactions are still at lab scales or within TRL5 and not at the commercially viable scale yet. Okay, the major drawback is the catalyst deactivation by cooking. Okay, now what are the steps for the cooking? At high temperature, what happens is CH4 breaks into elemental carbon and some hydrogen. Now this is an endothermic process, so that's favorable at high temperature. Then we have CO disproportionate reaction, which gives us again elemental carbon and oxygen, and this is an exothermic reaction, so this happens below 500 degrees Celsius. So the first reaction is mostly observed for the dry methane reforming reaction, whereas the second step is mostly observed for the reverse water gas shift reaction, where CO is our final product. Okay, now this elemental carbon can do different things. Now it can be hydrogenated to form methane gas and then just leaps to the gas phase, such that the carbon is gone from the surface, such that the deactivation does not happen for too long, it's a temporary deactivation, or with a longer stay at that temperature and pressure condition. Now this can convert to a polymeric carbon and then an graphitic carbon. The more the complex the structure of this carbon, the catalyst is more deactivated. It loses its activity more and more. Okay, what it further can do is that it can form a metal carbide type of structure. So instead of metal or metal oxide, which is desired for the CO2 reactions, now we have a metal carbide which poisons the catalyst. I mean, the catalyst structure is changed to a different structures because of the evolution during the reaction, and we lose the number of the active sites that we want for our reactions to happen, and that causes the deactivation. Another one is called a filamentous carbon. What happens is that our catalysts are porous in nature, right? So there are pores. So this carbon just sits inside the pore of the catalyst, and when it sits inside the pore of the catalyst, it just blocks. And once these pores are filled and more carbon are formed, the catalyst breaks. Okay, and because of these pore blockage, now access to the active sites of the catalyst is suppressed significantly. That's how the catalyst is deactivated. Okay, so now that we know the different steps for catalyst deactivation and this coke formation, now what we can do to eliminate these things? Okay, we can change in our process condition, we can change in our catalyst design, we can add a promoter. All these steps can be done together, or depending on the type of coke that we are forming, such that we can suppress the coking and keep our catalyst active for longer hours. Okay, the first step is oxidation. Simple, carbon is there, provide oxygen, it will burn, form CO2, leaves. Okay, but the problem is, if we use oxygen in a regeneration process, catalyst regeneration process, then it will oxidize our metals to metal oxide. Now metal oxides are not as active as the metals for CO2 hydrogenation reactions. So we change the nature of the catalyst, nature of the active site, so it does not really help. The other part is the CO2, it is a soft oxidant, so the CO2 can help in oxidizing some of the coke such that we form two CO molecules, right? So what we can do is that what is required by the stoichiometry of the reaction for CO2H2 ratio. If we provide little more amount of CO2 and tune the temperature and pressure a little bit, we can suppress the formation of the coke by a significant amount. Okay, the other thing is gasification, which I just showed. This elemental carbon is present here and it can be hydrogenated to form methane. Now for that gasification, we can provide a little bit of hydrogen if it is a dry reforming of methane reaction, or hydrogen is already present there for the other CO2 hydrogenation reaction, which can be utilized to form this gasification product, that is methane, such that the carbon is removed from the surface. Now this gasification happens at higher temperature like 500 to 700 degrees Celsius, and we can add a little bit of promoters, especially alkali promoters, which promotes the gasification process. Okay, so all these promoters can be added a little bit such that we can suppress the amount of carbon formation or the rate at which the carbon is deposited on the catalyst, because the carbon deposition is inevitable. But if we can suppress the rate at which it is deposited, or if we can increase the rate of removal, then we can keep our catalyst active for a longer durations. Now, there can be some of the other promoters that can help in suppressing the coke formation. Typically, some of the defect sites are selective towards the coke formation and does not take part in the catalytic reactions to that extent. So, can we add a promoter to selectively block those defect sites? Okay, so some of these promoters are potassium, tin, gold and sulfur, as well as moly, which has been implemented in various studies for the different reactions that we just saw, and very long catalyst stability up to 1000 hours and all have been seen instead of just 20-50 hours. Okay, and the other thing is, like, if we can get a smaller particle size of the active metal, smaller the particle, lesser the surface area available for the carbon chain to grow, and it's small, that means it can be oxidized or gasified easily. Okay, more polymeric structure and graphitic structure are the hard cokes, which are difficult to remove. More amorphous nature of the coke are easier to remove. They are called as the soft cokes. Okay. Now, this smaller particle size can be achieved by different ways. We can change the nature of the support. We can change the synthesis method such that the interaction between the support and the active metal is different, and because of that interaction, we can change the dispersion of the active metal on the support. Okay, we can do a support material modification, and here I am showing one simple example for the dry reforming of methane reaction. Here nickel is deposited on zirconia, and you can see the catalyst deactivates pretty fast. It's just 20 hours on stream, and the activity goes, say, from, if the starting is 1, it goes to like 0.05 or something, so 95% deactivation and all. If we go to nickel on alumina, the deactivation is slower, but it achieves the same final activity at a longer time. Okay, but if we mix zirconia and alumina, we have like a higher dispersion of nickel as well as the proper balance of acid and basic sites, such that there is some initial deactivation, but after a certain time the catalyst practically just performs in a stable manner. There is no more deactivation. Okay, so these are some of the steps that we discussed, like how the carbon is formed and how we can take different steps such that we can remove this coke and then keep our catalyst active for a longer time. And all these things are required for our CO2 hydrogenation practical feasibility. Okay, next is the heat management. Okay, and here I am putting the delta H of the reaction, or the heat of the reactions for the 4 reactions that we are discussing. We can see the CO2 methanation as an highly exothermic reaction. The CO2 hydrogenation to methanol is also an exothermic reactions. Exothermic reactions means they generate huge amount of heat during the reactions, and because that heat is generated, if it is not dissipated properly, it's going to increase the temperature of the catalyst bed and hot spots are going to be formed. And because of the hot spots, we are going to see structural modification of the catalyst, which will hamper detrimentally towards the overall activity. We can see sintering of the active particles and all these things. And on the reverse side, we have reverse water gas shift reaction and dry forming reaction, and they are endothermic in nature. That means we need to provide heat for these reaction to sustain on a steady state operations. Otherwise, there will be cold spots at certain part of the reactor if heat is not provided in a permissible fashions. Okay, so what can be done to dissipate heat here and what can be done to provide heat here? So we can have some kind of novel reactor mechanism. One is like a cell and tube reactor where we have a bunch of reaction tubes, and the particles inside these are not just any powder particles packed, but they are catalyst monoliths which have microchannels in them in return. Okay, that means whatever amount of heat that is being generated will be carried out by the coolant or the convective flow of the reactant at the same time. Okay, other mechanism is the fluidized bed reactor. So in this case, instead of a fixed catalyst bed, our catalyst particles are now in a fluidized motion, and because they are in a fluidized motion, the heat dissipation is more efficient compared to a fixed bed. But the only issue with this thing is that there is a wide distribution of the residence time of the reactants inside a reactor because of the fluidization, and hence it detrimentally affects the product distribution at the end. Okay, there are a couple of other approaches like microchannel reactors where we can have alternate reactant channel versus the coolant channel, or we can have stacks of reactant channels and coolant channels in different planes where we can dissipate heat in an effective manner. There can be plasma catalysis, which is another novel technique that is coming up by electrification, by charging the reactants at gas phase because of application of the plasma, such that we are not taking the reactor bed to the higher temperature for reaction to happen. Since we are at a lower temperature, this plasma catalysis can suppress the amount of heat that is being generated. Now, there can be novel ways of catalyst design. One is the catalyst monolith, which I discussed a little bit on the previous slide. We have microchannels. On those microchannels, we can deposit catalysts such that the catalysts are now not in a packed bed, but rather in a very porous media kind of thing, and then the flow of the convective flow of the reactants and the product through these channels are so efficient that they can take out the heat when the heat is being generated during the reaction on these catalyst particles. The other way is that we can have a very high conductive base on which we can deposit our catalyst. Now, here is an example that the thermal conductivity of silicon carbide is of the order of say 150 watt per meter Kelvin kind of thing, whereas SiO2 it's between 5 or 6 watt per meter Kelvin. So that's almost 2 orders of magnitude, 1.5 order of magnitude difference. And because of that, this top part will serve as the chemical promoter which does the reaction, whereas the bottom part is the heat dissipation medium. Okay. And here is just an example where we have different thickness of silicon oxide that is present on silicon carbide for methanation reaction and how that is affecting our reactions. As we can see, as I am increasing the SiO2 thickness on the silicon carbide, which is the high thermal conductivity material, the thermal conductivity of the overall material is going down, which is the blue curve here, and at the same time, even if my activity is not changing, my selectivity towards the methane, which is my desired product, is going down. That's because enough heat is not getting dissipated efficiently from the catalyst. That means at the molecular level or micro level, catalyst hotspots are formed and higher temperature is there, which promotes the side reaction, which is the reverse water gas shift reaction, and the selectivity towards CO is increased. Now, for endothermic reactions, we can have a similar reactor design like a cell and tube or microchannels, where instead of getting out the heat, we can provide heat to the reactor. But apart from that, we can have process electrification through microwave and Joule heating, right? So here, instead of any fossil fuel, which requires so much of the fuel to heat the material, and it's a bulk heating that goes from outside to the inside. So the outside is first heated and then the inside of the material is heated. But for the microwave, it selectively heats the microwave active material and it's an inside out kind of thing. And another heating process is the Joule heating, which is a resistive heating, is a different process. So we have thermal conductive material on which we are depositing the catalyst, right? And when we are passing current on that conducting material, because of the resistance of the material, heat is generated. And this electricity can be given from the renewable energy instead of any fossil fuels. Okay, and here is an example how the microwave heating versus the conventional heating for the dry reforming of methane, which is an highly endothermic reaction, the amount of energy input changes. So we can see when we are ramping up the temperature of the reactor to the desired temperature, that is from room temperature to 900 degrees Celsius, where we are doing the reaction, and maintaining the reactor bed or the catalyst bed at 900 degrees Celsius. For the same amount of methane conversion in both cases, we can see the heat required by the microwave heating is at least 100 to 10 times lower than compared to the conventional heating. Okay, so with these things we have another things where we are doing the thermodynamic limitations. That is because from the reactant we are forming the product. If we can effectively take out the product, then we can move the reaction to the forward direction. So couple of things there is a selective membrane which can remove the water that is formed, where the issue is that water, methanol, CO2 and H2 all have the same kinetic diameter. The other is like use of adsorbent with the catalyst which can absorb water, and since one of the product that we are taking out at the same time when the reaction is happening, the reaction can move in the forward directions. Okay, I think that's a good stopping point at this phase, and then we will just skip few of the things. And then that's just the summary. We have a bunch of different ways of designing the catalyst such that we can have these new ways of energy and chemical production. But at the same time, we need a highly active and selective catalyst as well as the reactor and the process design to see the commercial viability of these processes. Okay. Thank you.